Module 6, Lecture B, Classification Metrics. By the end of this lecture, you will be able to define accuracy as the fraction of correctly classified examples, construct simple confusion-style summaries from prediction results, and explain why accuracy alone may be insufficient in some classification problems. Understanding accuracy, correct prediction fraction. Accuracy in classification measures how often a model makes correct predictions out of all the predictions it makes. For example, if a model labels emails as spam or not spam, each email is either classified correctly or incorrectly. To find accuracy, you count how many emails were correctly classified and divide that by the total number of emails tested. This value tells you how frequently the model correctly identifies examples in the test set. Accuracy measures how often a model's predictions are correct. You compare each prediction to the true outcome and mark it as right or wrong. Then compute the fraction that are right. For example, if a medical tool makes 100 predictions and 80 match the true diagnoses, its accuracy is 80%. The same idea applies to systems like language learning apps or credit scoring tools, where accuracy reflects the proportion of correct decisions out of all predictions made. Model accuracy is measured as the fraction of correct predictions on a specific set of examples, such as a test set or real user interactions. Because this measure depends on the dataset used, changing the examples can change the reported accuracy even for the same model. For instance, a wildlife classifier might score high on clear images, but much lower on blurry ones. Therefore, accuracy always describes how well the model's predictions match reality within the particular context of the chosen data. Accuracy as percentage. Accuracy in classification is usually expressed as a percentage to make performance easy to understand and compare. It is calculated by taking the fraction of correct predictions and converting it into a percentage, such as saying a model that correctly labels 9 out of 10 emails as spam has 90% accuracy. Using percentages connects model performance to familiar ideas like exam scores or quality checks. This provides a clear, human-friendly summary of how well a classifier works on a data set. Expressing model accuracy as a percentage makes it easy to compare different models or versions of the same model. For example, saying one model is 87% accurate and another is 92% quickly shows which performs better. It also helps clearly communicate improvements over time, such as a medical model rising from 70 to 85% accuracy. In business settings, these percentages work well in dashboards and reports, giving concise summaries that support decision-making. Expressing accuracy as a percentage helps us see how a model's performance affects real-world outcomes. Even a system with 99% accuracy, such as credit card fraud detection, can misclassify many transactions when used on a huge number of cases. In medical screening, 95% accuracy still means some patients are misclassified, which may or may not be acceptable depending on the context. Converting between fractions and percentages makes accuracy easier to interpret and highlights how small percentage differences can have large effects when models are deployed at scale. Limits of accuracy. Accuracy is a common way to evaluate classification models, but it has important limitations. It only measures the overall proportion of correct predictions and treats all types of errors as equally important. In situations where some mistakes are much more serious, such as missing cases in medical screening for a rare disease, a model can appear highly accurate while still failing the people who are actually sick. This can create a false sense of reliability, so relying only on accuracy can lead to overconfidence in models used for critical decisions. Accuracy alone is not enough to judge a model's performance, because it does not distinguish between different types of errors or how they affect different groups. A spam filter, for example, might look accurate by labeling most emails as not spam, yet still let spam into the inbox or block important messages. Accuracy does not show whether there are many false positives or false negatives. In the same way, a credit scoring model can appear accurate overall, while consistently misclassifying certain demographic groups, creating fairness concerns that accuracy cannot reveal. Accuracy alone does not capture the real-world impact of model predictions because it ignores the different costs of errors and the role of decision thresholds. For example, in credit card fraud detection, falsely flagging a real purchase is inconvenient, but missing an actual fraud can be very costly. A model can have high accuracy yet still be poor in practice if it allows too many fraud cases to pass as normal. Since changing the decision threshold can shift the balance between different types of errors without changing overall accuracy, accuracy should always be evaluated alongside other metrics that reflect practical consequences. Classification error breakdown. Predicted class counts. To quickly summarize a classifier's behavior, you can count how many instances it predicts for each category, rather than looking only at overall accuracy. This means tracking how often each label is chosen, whether the prediction is right or wrong. For example, in spam detection, you count emails predicted as spam versus not spam, and in medical diagnosis, you count patients predicted as diseased versus healthy. These counts form a simple confusion-style summary that shows the model's decision distribution and prepares you for more detailed error analysis. Looking at how often a model predicts each class helps reveal whether it is using all labels fairly. If a review classifier mostly predicts positive and rarely predicts neutral or negative, it may be biased, perhaps because the training data were skewed. In the same way, a wildlife classifier might overlook rare species and group them into more common categories. Such imbalances suggest the model's predictions may not match real-world distributions and act as early warnings of potential problems. Predicted class counts help connect a model's behavior to real-world operational and ethical impacts. In credit scoring, for example, if many applicants are predicted as high risk, it directly influences how many loans are approved and how risk is managed. In public safety, the number of posts flagged by a model affects the workload for content moderation teams. Regularly reviewing these counts gives a high-level view of decision patterns and points you toward areas where more detailed error analysis is needed and where serious mistakes are most likely to occur. Python code, predicted class counts. This script gives a simple look at predicted class counts. It uses very small example predictions, so the idea stays clear. The main goal is to see how often each label appears in the predictions, and to focus on that counting process. We use the counter class from the collections module to quickly count how many times each element appears in a list or other iterable. In this script, it helps us tally how often each predicted label occurs in the dataset. This makes frequency analysis simpler, more efficient, and easier to interpret. We begin by creating a small list of predicted labels, where each item is a string representing a category from a classification task. In this example, the labels are spam and not spam, and they appear multiple times to represent several predictions. This simple setup gives us a collection of predicted categories that we can later analyze to see how often each label occurs in the results. The code extends the list of predicted labels by adding several entries marked as spam or not spam. It adds another not spam prediction, then a spam prediction, followed by 2 more not spam predictions. This sequence of labels is then used to study how often each type of prediction, spam or not spam, appears in the results. We first verify that the variable holding the predicted labels is actually a list, so we know the data has the expected structure before we use it. If it is not a list, we immediately raise a type error with a clear message explaining that it must be a list. This early validation step is important because it prevents later problems when we try to count or process the labels. We use the counter tool from the collections module to count how many times each label appears in the list of predicted labels. It quickly tallies occurrences and returns a structure similar to a dictionary, where each label is a key and its count is the value. This helps us understand the overall distribution of predictions and see which labels occur most often. We begin by turning the label counts into a list of pairs, where each pair contains a label and its corresponding count. This list is created using a method that returns all label and count combinations. We then sort this list based on the label, which is the first element in each pair. Sorting by label arranges the results in alphabetical order, making them easier to read and interpret. We first find the total number of predictions by measuring the length of the predicted labels list. This total is important because it serves as the denominator when we later compute how often each label occurs. By knowing the overall count, we can convert raw label frequencies into percentages. This allows us to describe each label's occurrence relative to the entire set of predictions in a precise way. Before doing any calculations, the code first checks whether there are 0 predictions. This matters because dividing by 0 would cause an error and stop the program. If the list of predictions is empty, it raises a value error to signal that at least one prediction is required. This safeguard helps prevent runtime errors and keeps the program running reliably. The code first prints a short header to introduce the summary of predicted class counts. This header tells the reader that the numbers that follow describe how many messages were classified into each category. By doing this, it clearly signals that the upcoming output is a summary of the predictions made by the small spam classifier. We examine each label and its count in the sorted list, and for each one, we compute what percentage of all predictions it represents by dividing its count by the total number of predictions and multiplying by 100. This percentage tells us how often that label was predicted overall. We then print a concise message that includes the label, how many times it appeared, and its share of the total. In this way, the loop provides a clear summary of the distribution of predicted labels. At the end, the script prints a summary line that reports the total number of predictions it processed. This final message clearly wraps up the output and makes it easy for anyone reviewing the results to see how many predictions were included. As a result, the scope of the analyzed data is immediately understood. This script examines a small set of predicted labels and counts how many times each one appears, such as spam and not spam. It uses a counting tool from the collections module to tally the labels, then sorts the results alphabetically. For each label, it computes what percentage of all predictions it represents. The script then reports the count and percentage for each label, along with the total number of predictions, giving a clear summary of how the predicted classes are distributed in the dataset. Per class outcomes. Instead of only looking at a classifier's overall accuracy, you can examine its performance for each individual class. For a given class, such as spam in an email filter, predictions fall into 4 groups: correctly identified, missed, wrongly flagged as present, and correctly rejected. This class-by-class view shows how well the model handles each category, rather than hiding everything in a single number. It is especially useful when different classes have different importance or consequences, because it lets you judge how effectively the model detects the specific cases you care about most. To analyze how a model performs on each class, treat one class at a time as the target and group all remaining classes as non-target. Then count how many examples of that target class are correctly predicted, how many are misclassified, how many non-target examples are incorrectly labeled as the target, and how many non-targets are correctly rejected. For instance, if you focus on bears in a wildlife classifier, you would tally correct bear predictions, bear images classified as something else, and errors involving non-bear images. Repeating this process for every class gives a clear summary of where the model is strong and where it struggles across different categories. Looking at model performance by class gives a much clearer picture than overall accuracy alone. In fraud detection, for example, you might see that the model catches fraud well in one region but misses it in another, or that it either overlooks true frauds or wrongly flags legitimate transactions. In language identification, it may work well for longer texts in common languages, but struggle with short or rare language samples. This kind of breakdown shows where the model works well, where it fails, and where you should focus improvements. Python code per class outcomes. This script examines how a classifier performs on each individual class. It starts by manually creating a very small example of predicted labels and true labels. Using this example, it then calculates confusion style counts for each class, such as how often each class is correctly or incorrectly predicted. The goal is to understand classification outcomes in a detailed, per-class way. The script starts by explaining that all the required libraries are already available in the Colab environment, so there is no need to install anything extra. This lets us begin working right away without setup delays. As a result, we can focus directly on the main task and benefit from a smoother, faster workflow, which is especially helpful in educational or exploratory work where quick experimentation is important. We begin by defining a list of true labels that represent the actual categories in a small dataset. This list has 6 entries, and each entry is one of 3 classes: bear, deer, or fox. These true labels act as the ground truth, meaning they describe the real, correct class for each example. We will use them to evaluate how closely a model's predicted labels match reality. We now define the predicted labels for our dataset, which are the model's outputs for each example. These predictions correspond to the true labels we specified earlier. By comparing predicted labels with true labels, we can evaluate how well the model performs on each class. This comparison allows us to compute metrics such as true positives and false negatives, which show how effectively the model distinguishes between different classes. To begin, we find all the unique classes in the true labels by turning the list of labels into a set, which automatically removes duplicates. We then convert this set back into a list so it can be sorted. Sorting the list gives the classes a consistent order, which is helpful for clear reporting and reliable comparisons later in the script. Before comparing true labels with predicted labels, we must confirm that both lists have the same length. Each true label needs a corresponding prediction for the evaluation to be valid. If the lengths do not match, it signals a data mismatch that could cause incorrect analysis or script errors. This simple check protects data integrity before any further computations are performed. We define a function that calculates how many outcomes fall into each class. To do this, we create 4 counters that start at 0. As we compare predicted labels to the true labels, these counters keep track of true positives, false negatives, false positives, and true negatives. This setup lets us systematically tally classification results for later evaluation. We examine each pair of true and predicted labels to see how they relate to a specific class. For every example, we check whether the true label is that class and whether the predicted label is also that class. These 2 checks tell us if the example truly belongs to the class and if the model assigned it to that class. Using this information, we can classify each example as a true positive false negative, or another outcome type based on how the true and predicted labels align for the class in question. The code tracks how each prediction compares to the true class by updating 4 counters. When both the true label and the predicted label match the current class, it counts a true positive. When the true label matches but the prediction does not, it counts a false negative. When the true label does not match but the prediction does, it counts a false positive. In all other cases, it counts a true negative. This process classifies every prediction into one of these 4 outcomes for confusion matrix analysis. The function finishes by returning a dictionary that summarizes the classification results. It includes 4 counts: true positives, false negatives, false positives, and true negatives. Each count is computed by comparing the true labels with the predicted labels for a specific class. This compact summary makes it easier to interpret how well the model performed for that class. The code first prints a short header describing the dataset, then displays the true labels alongside the model's predicted labels. This side-by-side view gives a quick snapshot of how well the predictions match the actual outcomes. It lets us visually compare results at a glance before moving on to more detailed analysis. We evaluate the model by going through each unique class in the dataset and measuring its performance separately. For every class, we use a function that takes the true labels, the predicted labels, and the current class as inputs. This function calculates how many predictions are true positives, false negatives, false positives, and true negatives. By doing this for each class, we can assess how well the model performs on every specific category. The code prints a brief summary of classification results for each class. For every class, it first shows the class name, then displays a dictionary of outcomes. This dictionary includes the counts of true positives, false negatives, false positives, and true negatives. Together, these values give a clear snapshot of how well the model performed for each class in the dataset. This script evaluates how well a classifier works on a small dataset with 3 classes: bear, deer, and fox. It compares the true labels to the predicted labels and calculates confusion matrix values such as true positives, false negatives, false positives, and true negatives for each class. When you run it, you get a summary for each class that shows how closely the predictions match the actual labels. This makes it easier to see where the model is performing well and where it is misclassifying examples. Finding systematic errors. Once you summarize your classification results in a confusion-style format, you can start seeing systematic errors instead of treating each mistake as isolated. These recurring misclassifications reveal problems with your data, features, or model decisions. For instance, if a medical system often predicts mild infection when the true label is early-stage cancer, that pattern shows a consistent confusion between those classes. By examining which true classes are frequently misclassified and where they are mapped, you turn a vague sense of errors into a clear picture of clustered mistake patterns. When you interpret confusion-style summaries, focus on what each class means in the real world. For instance, a spam filter that often flags promotional emails as spam, but rarely mislabels personal emails, reveals a systematic issue that could frustrate users. In credit scoring, if many medium-risk applicants are classified as high risk, they may be unfairly denied loans. These patterns show where the model's decision boundary does not match the real concept. By tying each type of error to its real-world impact, you can decide which mistakes are most urgent to fix. When your confusion-style summary reveals systematic errors, investigate why they occur and plan targeted fixes. Look for patterns, such as certain conditions or types of inputs where the model fails, which may point to gaps or biases in your data. For example, Repeated mistakes on specific kinds of text or images can signal over-reliance on limited cues. By combining the summary's quantitative patterns with a close look at representative examples, you can refine your data, features, or model design to better address these weaknesses. Why context matters. Imbalanced class pitfalls. Accuracy measures how often a classifier's predictions are correct, but relying on it alone can be misleading, especially when the classes are imbalanced. In situations like medical tests for rare diseases, a model that always predicts no disease could still achieve very high accuracy. However, such a model completely fails to detect the actual disease cases. This means the high accuracy mainly reflects performance on the common class, not the rare but often more important class. Therefore, accuracy by itself does not fully capture how effective a model is at finding critical, infrequent cases. This problem appears not only in medicine, but also in areas like fraud detection in banking and spam filtering in email, where the important class of interest is rare. A model that labels everything as normal can still show high accuracy because it mostly sees normal cases, but it completely misses the rare but critical events. From a business standpoint, even a single missed fraud can be very costly, and failing to catch spam can damage user trust. Therefore, relying on accuracy alone can be misleading because it does not show how well the model handles the minority class that matters most. When classes are imbalanced, accuracy alone can be misleading because two models with similar accuracy may treat the minority class very differently. One model might correctly find many minority cases but make more mistakes on the majority, while another might almost ignore the minority class yet look accurate overall. If we rely only on accuracy, we may choose a model that fails where it matters most. To avoid this, we need metrics that evaluate performance on each class, especially how well the model identifies positive cases and avoids false negatives, so we do not deploy models that look good in summary but perform poorly in critical situations. Python code, imbalanced class pitfalls. This script demonstrates how accuracy can be misleading when classes are imbalanced. It uses a small, medical-style disease example to show that a model can appear highly accurate while still performing poorly on the minority class. The focus is on understanding these pitfalls through accuracy and confusion matrix-style summaries. Overall, it highlights why we must look beyond simple accuracy when evaluating models on imbalanced data. This script runs using only the standard libraries that come with Python, so you do not need to install any extra packages. Because everything it uses is already included by default, you can execute it directly without additional setup. This makes it especially convenient to run in environments like Colab, where these libraries are already available and ready to use. We begin by importing the numerical library NumPy, which is used to handle arrays and perform fast numerical calculations. In this script, it manages arrays that store patient data and supports tasks such as shuffling entries and generating random values. This setup is essential for simulating the medical scenario and for evaluating how well the model performs. We begin by setting a fixed random seed using a function from NumPy so that any random operations in our script always produce the same results. This makes our work reproducible, meaning we can rerun the code and get identical outcomes. Reproducibility is especially important when working with randomness in simulations or when evaluating models, because it allows us and others to reliably compare and verify results. We begin by setting the number of patients in our dataset to 1,000, which defines the total sample size for our simulated medical scenario involving a rare disease. This fixed number provides a clear and consistent basis for all later steps in the analysis. It ensures that any labels, predictions, or other operations we create are all aligned with the same realistic dataset size. We begin by setting the number of patients who have the rare disease to 10. Next, we find the number of healthy patients by subtracting these 10 from the total number of patients. This gives us the count of patients without the disease and clearly separates the diseased and healthy groups for later analysis. We create an array of true labels to represent the actual health status of 1,000 patients. Using a numerical library, we combine 10 ones, which stand for patients with the disease, and 990 zeros, which stand for healthy patients. This produces a highly imbalanced dataset where the disease is rare compared to healthy cases. We then use this array as the ground truth to evaluate how well different models predict the patient's health status. The code uses a NumPy function to randomly shuffle the array of true labels so they are no longer in a fixed or predictable order. This creates a more realistic situation where data points arrive in a mixed sequence similar to real-world datasets. By removing any structured ordering, it helps ensure that the model's performance is evaluated more fairly and accurately. The code verifies that the array of true labels has the same size as the expected number of patients. This check confirms that the data is structured correctly before any further processing. By making sure the array has the right dimensions, it helps prevent errors later in the script. In this step, we build prediction outputs for Model A by assuming that every patient is healthy. We generate an array of zeros that matches the size of the true labels, so each prediction indicates no disease. This simple setup reflects the model's assumption that no one has the condition and allows us to later measure how well such a naive approach performs. In particular, it helps us evaluate accuracy and confusion metrics on an imbalanced dataset where most patients are actually healthy. In this example, Model B makes predictions by assigning each patient a random probability using a numerical random function. If a patient's random value is less than 0.02, the model predicts that the patient has the disease. Otherwise, it predicts they are healthy. This setup mimics a model that guesses the disease only rarely, matching the idea that the condition is uncommon. The final predictions are stored as zeros and ones, where 1 indicates a disease prediction. This part of the code defines a helper function that safely computes accuracy. It first checks that the true labels and predicted labels have the same shape, so they can be compared correctly. It then counts how many predictions match the true labels, and divides this count by the total number of predictions. The result is a simple accuracy value that reflects how well the model is performing. This function computes the 4 key parts of a confusion matrix used to evaluate a classification model. It first checks that the true labels and predicted labels match in size, so they can be compared correctly. It then counts true positives where both labels indicate disease, false negatives where the true label shows disease but the prediction does not, true negatives where both show no disease, and false positives where the true label shows no disease but the prediction incorrectly indicates disease. These 4 counts summarize how well the model is performing. We first measure the accuracy of Model A, which always predicts that every patient is healthy by using an accuracy function that compares its predictions to the true labels and computes the fraction of correct predictions. We then apply the same accuracy function to Model B, which makes random predictions with a small chance of predicting a disease. By comparing these 2 accuracy values, we can see how well each model performs in terms of overall correctness on the patient data. We summarize the confusion matrices for both models by using a function that counts true positives, false negatives, true negatives, and false positives. First, we apply it to Model A, which predicts every patient as healthy, to see how many cases it classifies correctly and incorrectly. Then we apply the same process to Model B, which makes random predictions. Comparing these results shows how each model performs in terms of correct and incorrect classifications. We are breaking down the confusion counts for two models so their performance is easier to interpret. For Model A, which labels every patient as healthy, we pull out the numbers of true positives, false negatives, true negatives, and false positives. We do the same for Model B, which makes random predictions. By unpacking these counts for each model, we can clearly see their performance metrics and directly compare how well they detect the disease. We compare the accuracy of two models for detecting disease. Model A always predicts that patients are healthy, and we report its accuracy rounded to 4 decimal places. Model B makes random guesses about whether the disease is present, and we also report its accuracy to 4 decimal places. This side-by-side comparison shows how well each model performs in terms of overall accuracy, even though they use very different prediction strategies. We now look at the confusion matrix counts for Model A, which include true positives, false negatives, true negatives, and false positives. These numbers summarize how often the model correctly detects the disease and how often it misses it. They also show how often the model correctly identifies healthy patients and how often it incorrectly labels them as having the disease. Together, these counts give us a clear picture of the model's overall performance. We now look at the confusion matrix summary for Model B, which shows the counts of true positives, false negatives, true negatives, and false positives. These values tell us how often the model correctly or incorrectly predicts the presence or absence of the disease. By examining these counts, we can judge how well Model B detects the minority class, which in this case is the disease, and assess its overall performance. The printed message highlights that even though the two models have similar accuracy, they differ greatly in how well they detect the disease, which is the minority class. This shows that accuracy alone can be misleading when classes are imbalanced. In such cases, a model may appear to perform well overall, while still failing to identify many disease cases. Therefore, it is important to look beyond accuracy and consider how well the model handles the less frequent class. This example shows why accuracy can be a poor metric for imbalanced datasets, such as a medical case where only a few patients have a rare disease. In a group of 1,000 patients, only 10 are actually sick, yet two very different models both reach about 99% accuracy. One model simply predicts that everyone is healthy and completely misses all diseased patients, while the other randomly predicts disease and finds only a few true cases. Even though their accuracies look similar, their ability to detect the disease is very different. This demonstrates that in imbalanced situations, we must look beyond accuracy and examine confusion matrix details, such as true positives and false negatives, to properly evaluate model performance. Error costs in classification. When evaluating a classifier, accuracy alone can be misleading because not all errors are equally serious. In a medical screening system, for example, a false negative that misses a disease can have severe health consequences, while a false positive may only lead to extra tests and anxiety. If we only count correct predictions, we ignore these differences and may optimize the model for the wrong goal. To build useful systems, we must consider the real-world impact of different types of errors and align the model with practical objectives. In many real-world tasks, different types of errors have very different costs, so accuracy alone can be misleading. In credit scoring, a false negative means rejecting a good customer and losing business, while a false positive means approving someone who may default and cause financial loss. In fraud detection, missing a fraudulent transaction can create serious financial and regulatory problems, whereas wrongly flagging a legitimate transaction mainly causes inconvenience. Because of these unequal consequences, a model that looks accurate overall might still be poor if it tends to make the most costly kinds of mistakes. When evaluating classifiers, we should not rely only on overall accuracy, but instead think about the different costs of different kinds of errors. In a spam filter, letting some spam through is usually less serious than sending important messages to the spam folder. In safety-critical systems like autonomous driving, failing to detect a real danger can be catastrophic, while a false alarm may only cause a brief slowdown. Because of these asymmetric consequences, the quality of a classifier depends on how well it balances these errors in context. Using evaluation metrics that reflect real-world costs leads to decisions that better match practical goals than accuracy alone. Selecting appropriate metrics. Choosing the right evaluation metric depends on the task, the data, and the real decisions your model will affect. Instead of looking for a single best metric, focus on which types of errors are most costly and how common each class is. In some applications, like medical screening for rare diseases, missing true cases is very harmful, so recall matters more than overall accuracy. In others, like spam filtering, wrongly flagging legitimate messages is worse, so precision is more important. Ultimately, you should select metrics based on the real-world impact of different errors, not just on a single accuracy number. When choosing evaluation metrics, it is important to consider class imbalance and how decision thresholds affect results. Precision and recall are especially useful when focusing on specific or rare classes, such as fraud. Combining them with a harmonic mean gives a single measure that balances missed positives and false alarms, often providing more insight than accuracy alone. By adjusting the decision threshold, for example in spam detection, you can see how performance changes and select a cutoff that matches stakeholders' tolerance for different types of errors, rather than relying on a single default setting. When choosing evaluation metrics, you need to balance how easy they are for stakeholders to understand with how much technical insight they provide. Simple measures, like the accuracy of positive predictions, are more intuitive, while metrics based on curves or averages may require explanation but reveal important performance details. In sensitive areas such as criminal justice, fairness across different groups must be considered, so metrics are often computed separately for each group. In industrial settings, engineers may emphasize missed defects and unnecessary rejections because they have different costs. Overall, a careful evaluation relies on a set of complementary metrics that reflect real-world priorities and ethical concerns. In this lecture, you learned to define accuracy as the fraction of correctly classified examples, construct simple confusion-style summaries from prediction results, and explain why accuracy alone may be insufficient in some classification problems. In the next module, Module 7, we will go over data preparation.
Thank you for your attention. See you all in the next lecture.